All right, so you have learned the interactions that happen. There's three. You've learned sort of what they do. Photoelectric gives us our subject contrast, our grayscale. Compton and coherent scatter give us noise or scatter. Hey, so of the two, Compton scatter and coherent scatter, which of the two accounts for most scattered radiation? Compton. 97% comes from Compton scatter. Good. You guys are doing really good at this. So let's talk about attenuation and subject contrast. We're going to learn this word. I've introduced this word a bunch. I usually give it to you in CPR. We talk about attenuation of like electricity in CPR. But anyways, let's talk about attenuation as it pertains to the X-ray beam. So the word attenuation is sort of synonymous with the word filtering. Okay, it is absorption or filtering of something. In this case, it's attenuation, partial absorption of the X-ray beam. So this picture to the right shows an X-ray beam. By the way, is our X-ray beam made of many energies or only one kind of energy? I mean, it's X-rays, but is it made of a wide range or a narrow range? Many, right? When we say that the X-ray beam is made of many different energies, is there a word we can plug in with that? Polyenergetic, okay? Or heterogeneous. Heterogeneous and polyenergetic mean the same thing, right? The X-ray beam is heterogeneous. However, so put a pin in that. The X-ray beam is heterogeneous. There it is. Boom. But however, to talk about attenuation, when we talk about the body, we're going to show a toy example where the X-ray beam is monoenergetic or homogeneous, okay? So in this example, your X-ray beam only has one energy, okay? It either passes through or doesn't in a certain body tissue, okay? So now, if the X-ray beam, let's say, attenuation of the beam by a homogeneous aluminum wedge, right? Wedge is homogeneous, so is the X-ray beam, okay? With different thicknesses, the X-ray beam will be more or less absorbed, okay? At increasing thicknesses, more of the X-ray beam is attenuated. And you might want to know, which we will cover, I won't give it to you right this moment, but you might want to know how much thickness increase, for a given thickness increase, how much of the beam is absorbed. And I'll give that to you in a minute. The thing to take away from this is, as more of the beam is absorbed, less of the beam is left in the remnant radiation, okay? The thickest part of the step wedge absorbs the most of the X-ray beam, so it's going to produce the whitest part of the image. The thinnest part of this step wedge absorbs the least radiation, so more of it's going to make it to the receptor, okay? The places where the body is thin lets more of the X-ray beam through. The places where the body is thick or dense also lets less of the X-ray beam through, okay? And we have different densities, different thicknesses and densities in the body. Attenuation is a cumulative effect of all three interactions, photoelectric, Compton, and coherent. Both absorption, photoelectric, and scatter, Compton and coherent, will prevent X-rays from reaching the image receptor. By the way, we talked about interactions, right? One of the options is no interaction, right? The X-ray beam just jams right on through the body. No interaction at all. That's one possible thing that can happen. Particulate radiation would not make it through the body, okay? The reason why we can make X-ray images is because we have a type of radiation that can penetrate through tissue, have some interactions, but also make it all the way through the tissue, right? We can't use visible light to make images of the body because visible light is absorbed by our bodies. You can prove that really easily by just looking up at me, right? You can't see through me to the whiteboard behind me, right? The light bouncing off the whiteboard coming towards you is caught by my body, and you get just the silhouette of me. Plus there's light bouncing off of me too, so you get to see what I look like. Unfortunately for you. Okay. Particulate radiation can't do that. Okay. Particulate radiation just is stopped by the body. And here's a reason why. Recall that X-rays are massless, chargeless, okay? Travel in straight lines, but importantly, they're massless and chargeless, okay? Particulate radiation coming from radioactive atoms are massive and charged. What do we know about electric charge? There's two types, like positive and negative, right? What do they do to each other, the charges? Cancel each other out. A large positive charge would do what to a negative charge? Attract it, right? And like charges would repel each other, right? So you've got a body full of electric charges, okay? And you've got a massive little particle of radiation that's electrically charged, okay? As soon as it interacts with the body, it's going to be pushed or pulled or attracted or pushed away from everything else in the body. It's going to be stopped almost immediately, okay? Just because of the electric charge. And on top of that, particulate radiation is massive. It's big. It runs into things, okay? So you cannot make images with particle beams, okay? You can use particle beams to do things like destroy cancers and stuff like that, but you can't make an image with a particle beam. Small asterisk there, because certain particulate radiations emitted from inside the body can produce an image, like positron emission tomography, PET scans. But under most circumstances, you can't take and make a particle beam and produce images at an image receptor. That's why we need X-rays. X-rays are still attenuated, though. They're absorbed as well as other things. They're absorbed less, though, than other things. Some of them make it to the image receptor. Recall that about only 1% of the primary beam exits the patient. 99% of the primary beam absorbs within the patient, is attenuated by the patient. X-rays are absorbed exponentially, reducing by a certain percentage for an incremental thickness increase in tissue, hypothetically never reaching zero. So here's a picture. I love this picture. It's one of my favorites because it teaches you the 4 centimeter rule. Okay. So this is the idea. Let me get rid of the words for a second and just zoom in on this. Okay. You're seeing slices of body tissue in 4 centimeter increases. Okay. The top of the body is shown up high and the bottom down low. Okay. Now, take the top of the image. You have 1,000 X-ray photons that are incident upon the surface of the body. 1,000 X-ray photons hit some little square area. We haven't said how big the area. It doesn't matter. Pass them through 4 centimeters of tissue, and exiting out the other side of that 4 centimeters of tissue, there's going to be about 500 photons. That means for every 4 centimeters of tissue, about half of the photons are absorbed. Okay. So 0 to 4 centimeters, you exit the 4 centimeter mark with 500 photons. Now 500 photons go through the next 4 centimeters of tissue, and what exits are half of the original amount. Now go through another 4 centimeters of tissue, and what exits are half of that amount. Each 4 centimeter of tissue cuts the intensity of the beam in half. So what do you do with that, right? You got to be able to do something with that information. So that's the idea. For every 4 centimeters of tissue thickness, the X-ray intensity reduces by about 50%. So for every 4-ish centimeter increase in part thickness, increase radiographic technique twice. Okay? Double the mass, or increase KVP by 15%. So let's work a couple of these through on the board here.